So what we did in the last class was something very important as digital designers, because we calculated the most important part of digital electronics, which is nothing but the delay calculations. Why delay calculations is important? Because that is what we are striving for. Any design that we make, it has to be fast enough. You cannot be a good designer by just designing the application. It has to be fast enough. It has to be efficient enough. So how do you know that it is fast enough? You have to calculate the delay or the time it takes for your inputs to travel to the output. So that is very important. So we just gave a very simple glimpse of how to calculate the delay, especially the gate delays for adders. We have been every time emphasizing on adders for the reason, as I said in the last class, because we are going to do all arithmetic operations using adders only. You want to perform a normal addition, adder is required. You want to perform a normal subtraction, again we perform subtraction using addition by taking 2's complement. We did a beautiful example also sometimes back. And then you want to perform multiplication. In multiplication also there involves an adder. You want to perform division, then you have to do shifting operation. Either you shift left or right, based on that you divide or you take modulus. Now, so that is the reason we have been emphasizing a lot on adders. So when adder has got so many applications, it is very important that we must remove all the disadvantages pertaining to adders that we are using. Now, every time we speak about the adder, the only problem that comes to our mind is the delay it takes, the time it takes for your carry to propagate. So the only adder that we know so far, they are called as ripple carry adders, or in short, we call them as RCAs. Now, what is the problem with the ripple carry adder? If it is a 4-bit adder, then if A3 and B3 are your most significant bits, then your carry that generates from this A3 and B3 block. A3 and B3 is nothing but the last block, right? So for a 4-bit adder, you will have A3 here and B3 here, right? So this is A3 and B3. So your carry out here will be C3, and obviously sum is also S3. This C3, it depends on the carry that comes from the previous stage, which is your C2. So that is the main disadvantage here. So A3 and B3 are available as input signals only after C2 is available, which means that you will get a meaningful outputs. You will get a meaningful output, that is C3 and S3 will be meaningful only when your C2 is available. Though A3 and B3 is already available at the start of your inputs itself. So till the time C2 is available, it doesn't mean that you will get a zero output. You will get some output, but they will be either a random output or they may be an incorrect output. Okay. So similarly, it is not only with this particular stage, it is also true for this particular stage also, meaning A2 and B2 must be waiting for A2 here and B2 here must. So, and this is S2, A2, B2 and S2, they will be waiting for your C1 in fact from the previous stage. So this is a huge problem, and you will get the final output of S3 and C3 only after all your carries have rippled through all the stages. Only after your carry from your C in gets rippled to first to C1 and then to C2 and then to C3. You will have to wait till that particular time. This is just for 4-bit. If you have 16 bits, if you have 8 bits, then your carry propagation is doubled. If you have 64 bits, then your carry propagation gets doubled by how many? 16 by 4 is 1, 2, 16 times. Your carry gets multiplied by 16 times, which we cannot keep waiting now. So what we are going to do is today, we are going to analyze how we can reduce this particular delay. If you want to analyze how we can reduce this particular delay, first let us consider the gate level logic of a full adder circuit. So you know that this is the full adder circuit. So this is a part of a half adder and this is one more half adder. And in addition to two half adders, you have one OR gate. You can implement a full adder circuit. So let us come back to that. Now, how are we going to analyze? First, let me define the certain variables here. I am going to consider the generalized inputs here. Hence, my inputs are AI and BI, and my carry in is also I, where this I here represents the stage, right? It may be a first stage, it may be second stage, third stage, depending on the kind of adder we have. If we have an n bit adder, then I can go from 1 to nth stage. And your outputs are your sum with a sum Ci, and obviously your carry will always be one carry stage ahead, because your first carry will be C0 and then your carry gets propagated from one stage. So to the other stage, your carry gets propagated. So it is Ci plus 1. So, and now we are going to define the intermediate stages also. What does this mean is, after this XOR of this AI and BI, we are going to define it as PI. Why PI? Why not some other variable? Because this P corresponds to propagate, right? Propagate. Hence, we are calling this as PI. And your carry here, if you look at how your sum output is getting carried away, first let us focus. We are in fact dissecting our complete circuit. So if you want to get an output across this sum, then how will your sum signals will get propagated? Your sum signal will get propagated directly from this one, right? So which means that this PI is a propagate signal which will propagate your AI and BI's input. That's what it means. If you look at the number of gate delays, right? This particular sum you will get just with an XOR I of, because nothing is going to stop this particular input to getting propagated, right? So the Ci is already available across this XOR gate here. Only time delay that it takes is for your Pi to propagate from this AI to BI, right? Only this particular gate delay. Once this is available, your Ci, your sum is just nothing but XOR of Pi and Ci, which means that the sum is not dependent on any other propagation of your carries. That is, any other previous stages carries, it is not dependent on. So which means that getting the sum output is slightly simple. So that is not we want, because the main culprit here is this particular carry getting propagated. So we must first analyze how your carry is getting propagated, and that is of interest to us, which means that this part of our circuit, which we just analyzed now, is least importance to us, because this is already creating a lesser delay only, just a 2 gate delays. So, but the one that creates a lot of delay through rippling effects is because this carry. So let us focus towards that particular carry. Till this particular point, is there any other doubt? Do you have any doubts till this? Because after this, we will have to again slightly deep jump into concepts. Okay, I believe there are no doubts. Okay, so there is no issue with this sum output now. Okay, now let us focus towards the carry. Look how your carry is getting propagated. So your carry propagates through this. First it reaches this AND gate. Okay. And then after this AND gate, it propagates through this OR gate. And then you get the output. So which means that if you want your carry to get propagated, it means your PI signal must be available. This is an AND gate, right? When will you get an output of an AND gate? Only when. So output of an AND gate, you know, 0001 1011 11000001. If one signal is CI and other signal is PI, if carry is available, only if your PI here is 1, only then you will get your carry getting propagated, right? Which means that this carry this carry will get propagated to the output of your AND gate only when your PI signal is available. Only when this particular signal is available, you will get this particular signal. Okay, and this and let us define another signal called as the generate signal, right? What is this generate signal? The generate signal is nothing but the AND of AI and BI. It means that this signal, in addition to this PI and carry CI, you will get across your output. This is just an OR operation only, but this PI will take an important part in allowing your carry to propagate to the next stage. So if we are getting a carry across this particular stage, if we are getting a carry signal here, it means that we can conclude that this PI signal is active. Okay, so this AND gate plays a very important role in allowing your carry to propagate to the next stage. Okay, so this is what is the logic behind. We are going to separate this carry signal alone, and then we are going to dissect. So there is a lot of theory behind. So let us, I've already covered the written theory that is below this particular diagram through my explanation, but still we will go through point by point and then we will understand much better. So here, what is written here is, so you know that subscript I here, your subscript I corresponds to the typical stage of the adder. Signals PI and GI, they will settle immediately when your gates are available. Am I right? Yes, because PA signal is this one, PA signal is this one, and GI signal is this one. And nothing stops this PI and GI because you just have one gate delay here. Okay, so they are a steady state signals here. So signals at PI and GI settle to their steady state values after they propagate through their respective gates. So there will be no issues in generating PI and GI. These two signals depends only on your addend and augment builds, which means that this PI and GI depends only on AI and BI, addend and augment. Okay, so hence there is no issues with these signals here. Signals from input carry CI to the output carry CI plus 1 have to propagate through an AND gate, the one that I deeply explained, and an OR gate, which constitutes a two gate delays. Am I right? So because if you want your signal to propagate from CI to CI plus 1, how many gate delays are there? It has to propagate first to this gate delay. So one gate delay here, and it has to propagate through another gate delay, one more gate delay here. So total two gate delays it has to travel. So if we, this is for a single bit adder. If it is for a 4-bit adder, then 4 into 2, it is 8 gate delays. If it is a 16-bit adder, then 32 gate delays. 64-bit adder, then 128 gate delays. Right? So this we all know. So which means that for an n-bit adder, the gate delay that will be required will be 2 times n, 2n, for your carry to propagate from input to the output stage. So our objective here is going to minimize this carry propagation time. So carry propagation time is an important parameter of your adder, which will determine the speed at which your two numbers are getting added. Okay, so any combinational circuit, either it may be an adder or any other circuit, will always have some values at the output terminals which will not be correct unless a steady state signal is arrived. Please let us note here that your output here, let me erase this because a lot of highlights have gone. Okay, so all right. So the output that you see here, that is once you switch on your circuit, once you switch on your circuit here, that is AI, BA, and CA are available, immediately within seconds or nanoseconds, you will have some output. But whether the output is right or wrong depends only after, we can say that only after all these signals have settled down in the circuit. See, when you switch on a tube light or even an incandescent bulb at your house, what happens at the starting when you switch on? It will just flicker for a few seconds and then it will glow. The reason behind is when you switch on your circuit, your current will not flow just as constant like this, but it will flow like it will create some transients. You must have studied in your double E, right? So it will create some transients like this. So which means that this part is the steady state part. So we have to wait till that particular time. So similarly here also in digital electronics also, if you want to have a correct output, you will have to allow all your other signals to settle down inside or to reach the stable state inside. So yes, and why we are again, I've already emphasized this particular point multiple times now. Why we are settling for only the adders, because all arithmetic operations are implemented by additions only or successive additions. So the time consumed by this addition process is very, very critical. And how do we solve this problem is we are going to look ahead your carry. We are going to predict your carry, or we are going to, instead of allowing your carry to propagate, we are going to calculate well in advance what could be the carry, right? So what is the logic behind? So we know that the two variables we have just defined, pi and gi. What is pi and gi? Instead of scrolling up, I have just copied here. What is pi and gi here? Pi is nothing but this one. Pi is nothing but ai xor bi. Similarly, this gi is nothing but what? ai and bi, right? So they are dependent on only addend and augment. Okay. Now, looking at the output sum, similarly, we can write our output sum also. It's already written. So your output sum depends on, don't include BI and BI again. This is because we have defined this to be a propagate signal. So it is just a PI XOR this input, which is nothing but your CI, XOR CI. So similarly, if CI is propagating here, this will be PI CI. And then your output here, CI plus 1 is equal to this generate GI, don't include AI, BI. So generate signal plus your propagate signal CI. All right. So these are our carry out signals. So our sum out carry out signals. So your GI is your carry generate. This GI, it will produce a carry of 1 when both your A and BA are 1, regardless of whatever input. So this is what I mentioned here. That is, your output here will be available only when your PI is equal to 1, which means that only when there are inputs, this A and BI available, right? Otherwise, this will not allow your carry to propagate. So your carry here depends on your PI signal to get propagated. Okay. So PI which is nothing but your carry propagate signal. This will not go to the next bit unless your this will not allow your carry bit to go unless this is equal to 1. Because this is the one, it determines whether carry in stage 1 must be propagated to carry to stage I plus 1. So PI will be true when an incoming carry is propagated. So we can always say that if a carry is getting propagated, we can now definitely say that AI and BI are 1, hence you are getting a carry. Okay, now this is some theory behind. Now how do we work upon? Consider the ripple carry equations we just saw. What is the carry equations we just saw? First, what is our objective here? What is the title of this particular topic we are discussing? The title of our topic we are discussing is carry look ahead generator. So we are going to concentrate only on the carry expressions. So what is the carry expressions we have? We can use this particular circuit also. Our carry expression that we have here is Ci plus 1 is nothing but Gi plus Pi Ci. Okay. Now, more importantly, we have to look at this part of your equation. The Ci plus 1 is dependent on this Ci. This is what we need to look at. Okay. Okay. Now, consider what is your C0 carry, because we are focusing only on carry here. C0 is nothing but your input carry Cin. Now C1, so the generalized expression here is Ci plus 1. So first, let us assume that we are having say four stages of your full adder. If you are having 4 stages of your full adder, so then I will be equal to 0, 1, 2, and 3. 4 different stages. So C0 is your input stage. So we will have, when I is 0, you will have C1 getting propagated to G0 plus P0 C0. When I is 2, then it will be C2 equal to G1 plus P1 C1. C3 will be equal to G2 plus P2 C2. What is the logic behind is, if you look this C1, it depends on C0. Similarly, C2 here depends on this C1 to get propagated here. Similarly, the C3 here depends on the C2 to get propagated. Instead, can we eliminate by substituting for the C1? If I substitute for the C1, let me take. If I substitute for this particular C1, Z0 and P0 C0, now your C2 will get directly dependent on your input. So if I write it like this, G1 plus P1 multiplied by G0 plus P0 C0, I'm eliminating this intermediate stage of C1, which means my carry 2 will be directly dependent on my carry in, which I know. Please remember that this C0 I very well know, which is nothing but my input signal. So similarly for C3 also, if I replace this C2 with G2 plus P2 multiplied by this whole expression G1 plus P1 G0 plus P1 P0 C0, right? What will happen? Just rearranging this, it is G2 plus G1 P2 plus G1 P0 plus P1 P0 C0. Now you see here that your C2 is dependent on C0 only, which is nothing but our known input. Your C3 here is dependent again on C0 only. Whereas this G1s and P1s, yeah, Gs and Ps, whereas all these Gs and Ps, they are directly available from our augment and addend. Okay, So this is the logic behind we are going to follow. So as I have mentioned here, this has been expanded here. Now, if you look, how does this equation look like to you? We have come across such equations multiple times. This is a product term. This is again a product term joined together with a sum term. A product term, product term, product term joined together with the sum terms. All these now are SOP expressions. How many levels of logic you require to implement an SOP expression? You require 2 levels of logic, if you remember. Am I right? So, which means that we have simplified. Again, still there is no reduction in the delay, but right, we are able to. There seems to be a doubt. Yeah, great. Okay. So, which means that we have not reduced our gate delays, but we are getting into a particular system of generating these carries with a 2-level logic here. So it is a 2-level logic and SOP expressions. So let us generalize this. So if you generalize this, the problem, so this is just to tell you how the generalized expression. If you would like to implement CI plus 2, no need to worry about this particular part, because this shows that the CI actually propagates to different cases through a ripple stages. So that is what is trying to uh, be told here. So you can see here that CI plus 1, CI plus 2 is dependent on CI plus 1, which is interdependent on CI. Again, CI plus 3 is dependent on this. So right? So this adds to a lot of delay, just to demonstrate this. Okay, which is nothing but the ripple propagation delay. All right. So now this is a generalized case here. If you implement this particular part, so a generalized case has been written here, right? So these are same expression. So no need to worry about this. Here I have given as C1, C2, C3, but here this has been generalized. Instead of C2, C3, this has been generalized as I plus 1 and I plus 2. So that is the only difference here. Otherwise, only thing that we need to note here is your one stage of your carry is dependent on your actual carry in input. This is your carry in input. So if you implement this, these are SOP expressions. You see here that this is your first level logic getting implemented, and this is your second level logic getting implemented. Right. So we have just flattened our expressions and we have implemented using just a 2-level gate. You can easily convert this into a NAND gate, right? So it is very simple to convert this into a NAND gate. Put a bubble here, put a bubble here, you put a bubble here, put a bubble. This will get converted to NAND implementation, right? So that is the only change. So if you are putting a bubble here, then this will be bar. Okay, so let's that is a simple thing that you can always do it. Okay, so now let us look at how to implement this 4-bit uh, carry lookahead generator. So we all have flattened these expressions, right? The same expressions which I have written here, not here. Yeah, which I have written here. So now is uh, is this going to speed up my operation, or how does it going to look like when I implement this using a gate level? So this will look like, this is how your gate level implementation will be. We will take one by one. So what is the expression for C1 here? C1 here is Z0 plus P0 C0. Just look at that. So C1 is here. C1 is here, which is nothing but G0, P0, C0, P0 and C0, right? And of this. And let us look at the next equation. C2, C2 is nothing but G1 plus P1 G0. We will come back to the next other part. So C2 is nothing but G1 plus, because this is an OR gate, G0 P1. G0 P1 is G0 goes from here, and P1 is your input signal here. Okay, and the other part, the last min term is P1, P0, C0. It is P1, P1 comes from here, P0 because this is what is our P0 is, and C0. C0 also we know, right? And these are ORed together to get C2. Okay, and obviously all these signals will come to the next stage also. You can see here. Okay, so now you have G2 here. Likewise, we can implement this. This is nothing but your combinational circuit, and all you need to look here is how many stages here. There are two stages here. What is the first stage? This is my first stage here, first stage, and my second stage. Two level logic we have implemented, right? Uh, and I hope this is clear till this. Please remember our topic of discussion today is carry look ahead generator. So which means our objective here is to generate the carries. Our objective here is to generate the carries. So just recall, have we generated our carries? Yes, we have generated our carries. C1, C2 and C3 are the carries we have generated. From where? From our new signals P2, G2, that is uh, the generators and the propagate signals. Generate signals and the propagate signals we have generated, right? Now, if you let me erase these highlights because yeah. Now, if you want to create a carry look ahead generator IC, right? IC means what? You will have some input ports, some output ports. So this will be a carry look ahead generator IC. Whether it is 4-bit or 8-bit, it all depends. The one that we have designed here is a 4-bit carry look ahead generator. So if this is an IC, what are its possible inputs here? Inputs are, look at the inputs, P2, G2, P1, G1, P0, C0 and G0. So which means I can always write my carry signal P0, P0, P1, P2, P3. This is a bad way of writing. I'll tell you a good way. These are also my input signals G0, G1, G2 and Z3. Z3 is not there. OK. And my other input signal, the most important signal is our carry in C0 or carry in. What are my output signals? C1, carry 1, carry 2 and carry 3. Because my objective is to generate a carry only, right? So I have created an IC now. So, but is my full adder complete? My full adder is still not complete because why? I'm generating only the carry here. So I have to, if you compare, where is my P's, G's and C's? Let me go back to your circuit here. Please see here, my P's, my G's and my C's are here, which means that I have tried to implement only this part of my circuit, right? I'm having a P signal here. Assume that this structure, this one, this symbol here corresponds to the IC symbol. So PI input I have to give, GI input I have to give, and I'm taking my carry output. And at the same time, if I want a sum, I have to connect an XOR gate here and then I have to get a sum. So if I want to generate a PI, I have to, if I'm using this carry look ahead IC, and if I want to convert that into a full adder circuit, then I have to give AI, BI inputs. I have to connect them through an XOR gate and an AND gate to generate PI and GI signals. CI obviously I will be giving, which is nothing but our Cin input. So that is what is being done here. So for a 4-bit adder with carry look ahead scheme, there is already an IC chip that is available in the market also, which is called as 74182 IC. Right? This IC is called as a look ahead adder IC. This will help us to build your full adder circuits. So if you want to generate the sum, how many XOR gates you want? You want two XOR gates. Okay. So which will one XOR gate will be helpful in generating PIs. One AND gate will be useful in generating GI. And in order for you to generate the sum, you need one more XOR gate. So the scheme here will be, so this is how your IC is going to look like. Am I right? See here, this is a 74192 IC. What are the inputs of your IC? C0, which is your input, C in, P0, G0, P1, G1, P2, G2, P3, G3. These are your inputs. C1, C2, C3, C4 are your carry outputs. So if you want to convert this into a full adder circuit, then all these P's and G's must get inputs from where? From through your XOR and AND gates of your different input variables. So A0, B0, AB, A1, B1, A2, B2, A3, B3. So what you get here is P3. Here you get G3. What you get here is P2, you get G2, P1, G1, likewise. So your carry is ready-made available. Your carry stage is ready-made available. If you want to take the output, all you need to do is just take the output here. So this is your C1. You take the separate output. This is your C2 stage. You take your separate output. This is your C3 stage, right? Okay. Now, if you want to generate your sums, then sum can be generated. Your sum can be generated through this XOR gate. Your sum can be generated through this XOR gate here. That is what is done here also. Through generate, and the other input of your P3 signal, other input of your XOR gate here is, I think I should erase a lot of. Okay. Okay. So the other input of for your sum to get generated is the carry input you are getting will be PI. So what we should do here, we must connect this P3 here to your input, which is very easy, an external connection only. Similarly, P2, you have to use a jump wire to connect to your input port. You connect this P1, again you have to use a jump wire to connect this P1. For P0 again, you can use a jump wire to connect this P0, right? So we have created a full adder circuit. Any doubt here? Okay. So this is a very uh, important design which we reduced our delay. You can find a lot of research papers, especially dealing with full adders, where attempt to reduce the delays were made. Right? Even one of your seniors also, they did a design of 16-bit full adder, a carry look ahead scheme, because this is just a 4-bit only, right? So she did a 16-bit, and we almost published even a research article also. Okay, right. So I hope if there is any doubt, I'll wait for 2 minutes. It can be a break also because lot of theory and explanations here. Again, I'll continue at 41. So till then, you may relax. If you have anything to ask, I'm waiting. Okay, I hope you have digested what is a carry look ahead adder is. So now, henceforth, it will be a very smooth sailing. Uh, there will be no too much of theory like this. It's all about design. So now let's take an example of a BCD to 7 segment decoder. You all know what is a BCD number is. BCD numbers are from 0 to 9. If you want to display this numbers in a 7 segment decoder, what is a 7 segment decoder is? It is a display device which will have 7 segments to display any number you want from 0 to 9. So the 7 uh, displays will look something like this, right? So you must have seen it. Maybe I can Google it also. So 7 segment display. Yeah, this looks like this. You must have seen. Yeah, you must have seen like this, right? So these are 7 segment displays. One thing that you need to observe here is a dot here also. After this display, every display here, there is a dot. Observe this because there can be an uh, uh, if it is a physical class, then there will be an assignment. Okay, now there will be no assignment. Okay. Now that is how your 7 segment display will look like. First, in our what is our objective? We want to display say 0 across this 7 segment display. There will be 7 segments you can see here. A, B, C, D, E, F, and G, right? Uh, so what is the problem statement here? Problem statement here is design a BCD to 7 segment decoder. So which means we must first create a truth table. First, we must identify what are the inputs. If you want to display from BCD to 7 segment decoder, what are the inputs of a BCD? Capital A, B, C, D, because there are 0 to 9 only, right? And 7 segment displays, what are the outputs here? There are 7 outputs here, that is small a, small b, small c, d, e, f, and g. These are your outputs and these are your inputs. Okay, now we are going to design this. Again, obviously, what we will do is we will list down all the possible inputs of your BCDs, that is 0, 0, 0, 0 till 1001, because this corresponds to 9. After this, they are all don't cares. We are not bothered about the other inputs. And then if you want to display 0, that is the decimal equivalent 0, then what are the displays must be on here? The displays that should be on here are your A must be on, B must be on, C must be on, D must be on, E must be on, and F must be on. G must be off. Okay. If you want to display 1, then only B and C must be on. If you want to display 2, then A must be on, B must be on, G must be on, E must be on, and D must be on. So this will display 2. If you want to display 3, then A, B, G is on, C is on, and D is on. Now this will look like a 3. If you want to display 4, then A need not be on. F will be on, G will be on, B will be on, and C will be on. You want to display 5, then A is on, F is on, G is on, C is on, and D is on. I hope now you understand, right? Okay, there are certain things that you need to remember here, that there will be 6 invalid combinations, right? So what are the 6 invalid combinations? Starting from 10102 to 1111, there are 6 invalid combinations. You have to decide what you want to display, right? If you want to display a 0, then you have to map these 1010s with 0000, which means that the corresponding 0 output must be displayed. Or you can in fact display some funny combinations, some combinations like something like this also you can display, right? Or you can display just a hyphen here where this is your G. You can display that. So this is how you have to decide. And okay, what will you do if either you can display it like this, or if you want to display some random inputs, then what you can do is you can assume that some don't care conditions can be kept. So that you have to decide. So this is how the 7 segment displays will display 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right. So these are the inputs. These are the outputs. Sorry. So first we have identified what are our inputs. Inputs are A, B, C, D, and outputs are small a to G. So we are having 9 input combinations of BCD. So these are your BCD inputs. So you can see here that if I want to display 0, 0, 0, 0, then the only thing that is not available here is I am not using G here. Okay. So A, B, C, D, E, F must be on. Hence A, B, C, D, E, F is on, 0 is off. Likewise, I create the truth table. Once I create the truth table, then I have to create K-maps. Please note here, as a first part, all my invalid inputs, I'm going to display zeros. All my invalid inputs. And it's not working. Okay. All right. So all my invalid inputs here, they are going to display it as zeros. So it all depends on you. If you want to display some random inputs, then you can put don't cares also. Doesn't mean. So by assuming that my invalid inputs 0 will be displayed, so I can create K-map. So this is for my A input, then for my B input, C input, I create my K-maps like this. I create the combinations. So I get the implementation expressions for these. So A, for me to display A, then the circuit will be A B bar C plus B bar C bar D bar plus A bar BD plus A bar C. Likewise, you can get the expressions here. You can also display don't cares. If you want to display for all the invalid inputs, if you want to display some random inputs, then you can put don't cares also. Or some people will like 6 to be displayed. Uh, Instead of like this, you would like to display it like this. So then your equation will change. Okay. So these are different exercises, and these are some playful exercises. Okay, so you can perform. You can get it at your home also. You can order the 7 segment displays and the breadboards uh, at your home, and then you can just perform these experiments. So if you use don't cares, then your expression will get in fact simpler, but it will look odd if you are generating the invalid inputs, because you cannot expect that what kind of output you are going to get. So this is 2 examples that I have done, one with the don't care and other with the 0 inputs. So if you want to expand your learning on uh, 7 segment displays, you can also work on the dot matrix display as you see it in your mobiles or in your calculators, right? So that will be a bigger exercise. In a dot matrix display, I'm not sure how many dots are there. At least 25 dots will be there, I believe, right? So for all these 25 dots, you will have to create displays here, so that, and you have to select which are the inputs will be, which are the output LEDs will be on, which will be off. So that is a complicated display, but if you want, you can design. So this is one exercise that you can try. Another exercise that you can try is, if you want to have a display of negative numbers also, that is also possible, right? You want to create -9 to +9. that is also possible. How you can how that is possible? You can have such kind of a two displays here, right? One display you can use it for showing whether it is a positive number or a negative number, and the second display you can use it for the displaying the number. So again, it all matters only in the truth table how you are going to map. Okay, so if it is a so if you want to represent a negative number also, then you will have additional column for a negative number. And instead of A, B, C, D, E, F, G, you will have A2, B2, C2, D2 likewise for the second 7 segment display. And for the first 7 segment display, only G1 will be there because G1 will be on for all negative numbers. So likewise, you can play around with these digital circuits, right? So these are some of the mind trickling examples that you can think of. I think we will stop here. Henceforth, we are going to look at interesting medium scale integrated circuits, something like decoder, encoder, multiplexer, and demultiplexers. So I hope it is fine. So from next class, it's all about mostly about these designs of these circuits. So if there are no doubts, you can wind up. If there are doubts, you may stay. Great.